All right. So this is going to be a presentation on Archimedes' proof of the volume of the conoid, in particular showing that a paraboloid is 1.5 times the cone, which has the same base and the same axis as the paraboloid, or the way that I kind of think of it, the paraboloid is 1.5 times the cone that is contained within it. Before we jump into that proof, there's sort of this preliminary statement that I want to make because there's a very key point in the proof where Archimedes uses something called the law of the lever. I'm obviously not here going to prove the law of the lever, but I'm just going to state it. So the law of the lever states that if there are two weights, W1 and W2, on a bar of balance, then this bar will be balanced if their respective distances from the fulcrum satisfy the equation D1 times W1 equals D2 times W2. So this is sort of what that looks like. As long as D1, the distance of weight 1 to the fulcrum, D1 times W1 is equal to D2 times W2, this bar will be perfectly balanced. Okay, so to jump into the proof, we begin obviously with our paraboloid in question, and this diagram here, this is just kind of like a side view of the paraboloid. So we want to imagine that this is sort of like a three-dimensional sort of a bullet figure, but we're just looking at it from the side so we can see so it looks like the two-dimensional profile of it. So we have our paraboloid, which is BAC, which for us just looks like a parabola, and we imagine a cross section of this paraboloid to give this side view. And the axis of this paraboloid is AD. So the first thing that we'll do is we extend AD beyond the vertex, beyond A, to the point H, so that AH is equal to AD. And then we're going to imagine that HD, this full line HD, is a bar of balance with A as its fulcrum. Suppose that we have contained within our paraboloid a cone, which is in green over here. We actually won't work with this, surprisingly, we won't work with this cone at all until the very last step. Even though we're proving a relationship between the paraboloid and the cone, we don't work with the cone at all until the very last step. So, but in any case, we will work with the cone. So imagine that there is this cone in green that is contained inside the paraboloid. And suppose further that outside of the paraboloid itself is contained within a cylinder, which is in red, where the cylinder has bases B, C, and EF, and axis AD. And now what we want to do is we want to imagine a plane cutting the cylinder perpendicular to AD. So this plane is MN. So remember, even though this is a two-dimensional figure, we're looking at this as a side view. We want to, in our heads, picture this as a three-dimensional figure. And then we take a plane that cuts straight down through that three-dimensional figure. That plane runs perpendicularly to AD. So, and the plane again is MN. And this plane, when it cuts through really all of these figures, but in particular, when it cuts through the cylinder and the paraboloid, it's going to make two circular regions. One is the circular region that is cut out of the cylinder, which has diameter MN. The other is the circular region that is cut out of the paraboloid, which has diameter OP. So just kind of bringing things back to our modern notation as maybe a little bit easier way to think about some of the relationships in this figure that we're going to talk about. If we think about our parabola as being defined by the equation x equals y squared, disregarding the orientation, because obviously if A was like the origin of a Cartesian plot, this would actually be x equals negative y squared. So disregarding the orientation of the parabola, if we think of the parabola being defined by the equation x equals y squared, then we can note the following relationship between our segments, that this line segment AD, which we can think of as sort of like an x coordinate over here at D, AD is equal to BD squared. So BD is the y coordinate. Again, x equals y squared. So x is AD equals BD squared, the y squared. And similarly, AS is equal to OS squared. So then we have the following relationship of ratios that if we just take AD, or here I wrote it as DA, dA divided by AS is equal to BD squared divided by OS squared. And this is our modern notation, written in the notation that would be maybe a little bit more familiar to Archimedes. It's this colon notation, which in my head, for whatever reason, I can't help but to read this as an analogy, that dA is to AS as BD squared is to OS squared. By construction, we created HA, the line HA, to be equal to dA. And similarly, by construction, the line MS right here, the radius of this, the radius of the circular region cut from the cylinder, MS, is by construction equal to BD. So then we can rewrite this exact same relationship to say HA is to AS as MS squared is to OS squared. And because MS and OS are, again, the radii of the circular cross sections that are cut from our cylinder and our paraboloid, respectively, we then have the relationship that HA is to AS as the circle with radius MS is to the circle of radius OS. But the circle of radius MS is the circle in the cylinder, the circle that's been cut out of the cylinder. The circle with radius OS is the circle in the paraboloid. So in our modern notation, again, we might write something like HA divided by AS is equal to a circle in the cylinder divided by a circle in the paraboloid. And again, Archimedes would have kind of written it this way. HA is to AS as the circle in the cylinder is to the circle in the paraboloid. But writing it in this modern notation, it's a little bit easier for us to manipulate this equation to obtain this equation down here at the bottom, that HA, and this is just cross multiplication, basically. HA times the circle in the paraboloid is equal to AS times the circle in the cylinder. And we want to write it in this way because thinking of it this way, we're in a position to eventually invoke the law of the lever, Archimedes' law of the lever. So again, just rewriting the equation that we had on the last slide, HA times the circle in the paraboloid is equal to AS times the circle in the cylinder. And the reason that we can invoke the law of the levers is because we can think of the circle in the paraboloid and the circle in the cylinder as having some kind of weight. Even though it's an infinitesimal weight, we think of it as having some kind of weight. And then now this equation perfectly satisfies the law of the lever because it's saying that if we take the circle in the paraboloid and we put that at a distance of HA from the fulcrum, so right here on the diagram, here's the circle in the paraboloid, and it's placed at a distance of HA from the fulcrum, then that will balance perfectly with the circle in the cylinder at a distance of AS from the fulcrum. So all this is really kind of saying is that if we take the circle in the paraboloid in our graph and we hang it at H, then it will balance perfectly with the cylinder, the circle in the cylinder left where it's at. And since we chose this slice, MN, remember MN is the plane that's cutting down through our paraboloid. Since we chose this slice MN arbitrarily, it follows that this balance is maintained for every such slice. So if we completely sliced our cylinder and our paraboloid in this way, and then we proceeded to hang all of those paraboloid slices, like slide them over on the bar of balance and hang them all over here at H, while we left the cylinder slices where they're at, so basically just leaving the cylinder as it is, then we arrive at the conclusion that the cylinder, where it's at, is balanced perfectly with the paraboloid when the paraboloid is hung with its center of gravity at H. So here's kind of what that diagram looks like. Here's how that bar of balance looks. Now, if K, right here, if K is the midpoints of AD, then K is the midpoints of the axis of the cylinder, which means that K is the center of gravity of the cylinder. So by the law of the levers, we have then that HA times the paraboloid. So again, imagine that the paraboloid is just sort of being hung over here from H. HA times the paraboloid is equal to AK times the cylinder. And again, just manipulating this is the modern notation. This isn't how Archimedes would have written all of this all out. In the modern notation, this is the same as saying HA divided by AK is equal to the cylinder divided by the paraboloid, which in Archimedes' notation would have been this colon notation right here. HA is to AK as the cylinder is to the paraboloid. But by construction, AK is half of AD. K is the midpoint of AD. So AK is half of AD. And AD by construction is equal to HA, which means that HA is twice the length of AK. So the relationship here is 2 to 1. HA to AK is 2 to 1, which means that on the right-hand side, the same relationship is maintained. The cylinder to the paraboloid is 2 to 1. So in other words, the cylinder is twice the paraboloid. Cylinder equals 2 times paraboloid. And now we're going to use a proposition from Euclid's Elements. So from Book 12, Proposition 10, we have that any cone, the way it's stated is, any cone is a third part of the cylinder with the same base and equal height. Meaning that a cone is 1/3 of the cylinder that kind of contains it. So now we're actually talking about the cone that we wanted to be talking about this entire time. So what this is saying is that this cone, the green cone BAC, is 1/3 of the cylinder, or stated differently, the cylinder is 3 times the cone ABC. And since we previously found that the cylinder is also 2 times the paraboloid, just setting these two equations equal to each other, we have that 2 times the paraboloid is equal to 3 times the cone. So just divide through by 2, and we have that the paraboloid is equal to 3/2 of the cone ABC, or 1.5. So the paraboloid is 1.5 the cone ABC that is contained inside of it, which is what we set out to prove to begin with.